Hello, so here in this we're going to be looking at section 6.3. This is going to be continuing our work with different radicals and radical expressions, but this time we're going to be bringing in addition and subtraction, which if you look back to the previous sections of 6.1 and 6.2, you may have noticed that amongst all of those problem sets, we really did not have any addition or subtraction signs. We had some plus or minus signs, but in terms of addition and subtraction, they weren't there, saving it for this section. So like radicals, so radical expressions have the same. So this is about to outline the two things that have to be true for something to be like terms. Right? So when it says like radicals here, we're really talking about like terms, but like terms that contain radicals. All right, in order for them to be like terms, they have to have the exact same index. All right, that's similar to the previous sections. Square roots go with square roots, cube roots with cube roots. But when we're adding and subtracting, they also have to have the same radicands. And if you're curious about what that was, radicands are, regardless of the index, radicand is the terms underneath that radical sign. All right, so both of those things have to be in place in order for us to be able to add and subtract things together. And we'll see why, and that should make pretty good sense. It's going to be just like regular like terms. Before we even get onto this box, what will be, if we're comparing this back to like terms, some previous examples of like terms we've seen is maybe a 4x squared plus a 3x squared, right? And then what would that become? Well, we'd add those coefficients together, and we get a 7x squared. So things that are not like terms, 4x plus 3y, those aren't like terms because they don't have the same variables, right? And then there's lots of instances of things that aren't like terms. Even something like this wouldn't be like terms. If I give us 4x squared plus 2x, those aren't like terms because they don't have the same degree. Right, so that's going to be the same concept today. In order for things to add together, they have to have the same index and the same radicand underneath. All right, so this text box here is going to be the example out of our book to where it's just going to be using variables. So it's saying, hey, if we have any type of index, could be square root, cube root, root, where we have in there, and we have these same concepts underneath. So I'm just going to call it x in this case. But now we're going to be adding up the coefficients. So there'll be terms out in front such as a and b. All right, and then the summarized version of this is, it's going to be whatever a plus b is, because we'll add up those coefficient terms. The index will stay the same, as will the radicands. And so, just like the examples we saw above, this would be no different than having 3x plus 4x to give us a 7x. Right? That's 7 being the 3 plus 4, and the x is unchanged. Because when we're adding up like terms, or like terms being the nth root of x here on both, the variable doesn't change when we add them up. The only thing that changes is that we add up those coefficients. And this might look confusing in these examples, but when we get down to it here in a minute, it's quite simple. And this is true as well for subtraction, to where if we have any type of root that's the same things underneath, and we've got some coefficients with them, this would summarize to be a subtract b, leaving your radical expression the exact same. So when we move down to these, it'll be, a lot easier to kind of see this rule come into play. Now, the tricky part on this, though, is not getting it confused with last sections. So let's go ahead and jump into this first example. Here's what we would not do. I'm not going to interact this 5x and 5x with multiplication in any way, shape, or form because they are being added together. Right? The 5x and 5x will not multiply because they are not being multiplied. We can see that big addition sign in between. Instead, this is the 6.3 section, to where all we'll have to do is this. Let's identify here for us Square root of 5x is the same thing as square root of 5x. So now we simply combine our coefficients to get a 9 square root of 5x. All right? And if this confuses you, just think back to a regular old combining like terms. 3x plus 4x is 7x. The x is remaining unchanged, just like here for us. The 3 and the 6 combine with the difference of a 9, but the square root will stay the same. All right? Now, this section will open up a lot of these to where we just can't do anything with them. This would be that example of where this is already fully simplified. Right? There's nothing else further that we can do because we have different radicands here. All right, there's nothing I can do for this problem because the 5 and the 3 are not the same concept underneath. So that one is in final form already. All right, and then there's also the example of 3 here to where these won't be able to go together either. These can't go together because different indexes. So it has to be pretty specific for us to be able to add our radical expressions together. This one's also in final form because the 4th root and 5th root are different. They do have matching radicands, but they're under different roots, so we can't do it. All right, so don't be afraid on this section to have some where we're not able to put them together. They have to have both of these things at the same time. All right? All right, so looking here on this one, this is another example, once again, that we would not be able to do anything with these because we have different radicands, right? The x and the y are different, so this one's also already in final form. So it does take both of those components. All right? Now, with this here, sometimes they will be hidden. You know, when you initially look at them, they'll look like there's no way they're going to be able to go together, but then after you do some simplifying, that may or may not be the case. And this is where this is going to come in 6.1 and 6.2, a lot of the different practice that we've done. Because when you look at this problem initially, you'll recognize right away we don't have the same radicands on any of these. However, you might also recognize that these two components aren't fully simplified. So before you make any decisions about can we add things together or not, you have to decide first, are the different pieces fully simplified? Now, on these previous examples that we just looked at, I made sure that they were all fully simplified before we even jumped in, but we're now moving on to the next type. So for this one, I'd be able to think of this in terms of perfect squares. So the square root within 27, we could have 9 times 3. Within 48, we could have 16 times 3. And then when we go in and take the square root of the 9, the square root of the 16, what we'll end up with here is a 3 square root of 3 plus a 4 square root of 3, and then subtract a square root of 3. So after we simplify that, you might recognize, oh, now we do in fact have the same indexes, right? They're all square roots, and they all have the same index. Now, this might look confusing to you because there's a lot of stuff going on, but at this point now, all we're keeping track of are these coefficients. So the only math that we have to do now is what's 3 plus 4 subtract 2? So 3 plus 4 is 7, subtract 2 is 5, and the square root of 3 stays the same all throughout. Because we're just adding up pieces, so it's like you had 3 of something, you had 4 more of that same something to get 7 of it, then you lost 2 of it, leaving us with that final amount of 5. Right? So the components don't change, the radicand and index don't change when we're adding and subtracting. All right, so let's go through here and simplify the following. So that was the answer. I put that in the box. The word that goes here is going to be simplify. All right, now the reason it's important to simplify, this original problem was not ready with the same radicands and indexes. Once we simplified it, however, then it was. All right, so when looking at this one, a quick check-in to make sure we're not getting this confused with previous sections. It's common sometimes for me to have people add the inside components on these together, right? Which is tempting, as in the last sections we were always multiplying those inside pieces. But addition requires, a lot more specific pieces to be in place. So we are not able to simply add those two things up together, the radicands up in that sense. Instead, we have to simplify them first. So this one could be 9 and 2. This one could be 16 and 2. When we square root here, we will get 3 square root of 2 plus 4 square root of 2. And then we'd end up with a 7 square root of 2. Because we add up those coefficients. And if this is confusing you, think of this. I'm going to draw a picture here maybe to help you out. Because sometimes people get confused on why these don't go together in any way, shape, or form. This is just regular old like terms here. So if we think of this as we have 3 apples and we added with 4 more apples, and apples is the same for both because it's the same radicand, you'd have 7 apples. And that's why it's not 7 apples squared, or, not changing apples to any other type of fruit. You have 3 of something plus 4 of something, you get 7 of that same something. And in this case, that something was the square root of 2. All right, and we had 7 of it. All right? So that simplifying step is important. Even when we have different indexes, we'll have to go through and simplify it all the way down here first, and then see about if we have any radicands that are the same. Because on these here, the indexes are the same, so that's step 1. Let's get these simplified and see if the radicands then become similar. These being fourth roots might be a little bit harder to track down, but let's discuss that as well. So when we're looking at this, we want to look for perfect fourth roots. So I would take that 324, and I'm just going to start dividing it by some of my perfect fourth roots and see if we can get any simplifying. Now, 2 to the fourth root, if we divide it by that, which 2 to the fourth power is 16, 324 does not divide evenly by the 16. So we could try 3 to the fourth, which is an 81, and that one works. All right, and once again, I got that from just trying 324 divided by either 3 to the fourth or 81. They're the same. So 81 and 4 is left over. Then we're going to fourth root the 81, right? So not the square root for a 9, but this is a fourth root. So we'd have 3, because that's the fourth root of 81, with a fourth root of 4 left over. And we're subtracting it. Now, if these are going to go together, they're going to have the same radicand. So I'm actually going to divide 2,500 by 4 to see if this would even be possible for me to interact these. And the reason I'm picking 4 is because these have to match. So I'm going to go ahead and assume that 4 is in there. And when I try it, I get 625, which is a perfect fourth root. It's a perfect fourth root for 5. So we then have 5, fourth root of 4. And then this is a simple 3 minus 5 to get us a negative 2, fourth root of 4. All right, so always simplify these first before you make any conclusions on if you can simplify these or not.